So let's get started for the last talk of the afternoon session with Nathan Geist on completing and extending shellings of vertex decomposable complexes. Please. I'm afraid we don't hear you. No.
Not muted, but we can't hear.
No.
All right, that's not better. Now we also can't see. Nope.
Noted.
We don't hear anything. Hello, I'll try again. Okay, so does your computer have maybe a microphone that works without the headphones? So everything else works and you can hear us. All right. Okay, so there are many options. You can try to, so maybe you can join the Zoom call from your phone. Then you can, so if video and screen sharing works.
Stupid comment. Did you check the volume of your microphone? That might be it.
Still don't hear you. The good thing is you can curse as much as you want currently.
Have you tried select a microphone and circling through all the options?
Yes.
Ah, now we hear you.
No.
Okay. Is that?
We just heard you for a minute.
Try again.
No, Sherio, it's like.
How is this?
And it's gone. You should ask how it's possible.
How about now?
So far, so good.
Hello, every once in a while we hear a syllable.
This was an excellent question.
And now you're going.
Could this be physical, like some connection being We heard an ah.
Try again. Try again.
How about now?
Yes.
We hear something for now. Maybe
Continue.
a longer sentence.
Yes, the problem.
Yeah, no.
No.
Two words at most.
Maybe try a tablet, iPad, or whatever.
What about now?
We hear something
Is it?
and you're gone. All right.
It's in the audio settings. If you look at the arrow to the right of the mute button, one of the options is audio settings. And then it says suppress background noise.
Mm-hmm. Nope.
Well, we heard a nope.
No, that was me.
Ah.
Okay, how about this?
Yeah, longer
Oh.
sentence.
We heard the whole sentence. Good.
Okay, is it good now, or do you need it louder?
Quick.
It's
Fine.
good now.
Continue.
Yes.
Continue.
It's good.
Very good.
Okay. I apologize for that. That has never happened.
Don't worry, it won't be the last.
Okay, I'll begin now.
Screen sharing.
Show your screen. Show your screen.
Yes, please butt in if something happens.
We will. All right, so let me try again. So pretending nothing happened, I'm happy to have Nathan Geist for the last talk of the afternoon session on completing and extending shellings of Vertex decomposable complexes. We're happy to hear your talk.
Yes, thank you, Rama. And thank you to all the organizers for inviting me to speak here today and for their hard work in putting on the conference. Today, I'll be talking about some work I did jointly with Michaela Coleman at UGA, Anton Doctorman, and Suho Oh at Texas State University. And I should say that I'm a fourth-year undergraduate at Duke University. So today I'll be talking about the paper we wrote together on completing and extending shellings of Vertex decomposable complexes. So we'll talk about our main result and also some of the applications to matroids and Simon's conjecture. So just some brief definitions that many of you are familiar with. Simplicial complex on a ground set V is just a collection of subsets of that ground set such that it's closed under taking subsets. And by convention, the dimension of the complex is the cardinality of a maximal element, maximal under inclusion, -1. And throughout the talk, most of the complexes I talk about will be pure, so all the maximal elements will have the same cardinality. And also, I will call elements of the complex faces, but maximal elements facets. So we care about these because their combinatorial structure allows us to compute algebraic invariance, and we know how to study them using Stanley-Reisner rings. To each complex is associated such a ring. At the bottom, I'll give you an example of some notation being used. We have, in brackets, complex generated by two facets, two-dimensional complex The two facets are 1, 2, 3, and 4, 5, 6. And on the bottom right, I've written out all the elements in the simplicial complex. Must include all the subsets. So it'll be often easier to define the complex in terms of the facets. An important subclass of complexes that we were interested in are shellable complexes. So if the complex is pure, we say it's shellable if there's sort of this nice way to build it up. That means there's an ordering of the facets such that for each facet fk, the union of the previous facets, that intersection with fk is pure of dimension strictly 1 less. So here on the bottom, I have some pictures for you to think about. So on the bottom left is a shellable complex, and I've given you a shelling order. So F1, F2, F3, F4, F5. And you can check that at each step when you're adding a new facet, that the intersection with the preceding facets is just an edge. So it's a one-dimensional pure complex. And that's not even the only shelling order. But on the right, there is a problem because the complex is not shellable. Here's an example of an ordering that doesn't work. You start with F1, F2, F3, F4, but by the time you try to add F5, you notice that the intersection with the preceding facets just consists of an isolated vertex and the edge with F4. That's not pure, and even if F5 wasn't adjacent to F4, it would be pure, the intersection would be pure but not have the right dimension. So this is not shellable, and you can show that there's actually no ordering you can use. So why were we interested in this? Well, we know about the topology of the shellable complexes. They're just wedges of spheres or just contractile, as in the last slide. If we know a complex is shellable, then we immediately know its Stanley-Reisner ring is Cohen-Macaulay. So there's a nice algebraic interpretation. And at the bottom here, it's also fairly simple to get the H vector if you have a shelling order in mind. By easy, I mean you don't have to get the F vector first, but there's just a nice interpretation that way. Some examples that are known, the boundaries of simplicial polytopes are shellable. That's a fairly classic result of Bruggesser and Mani using a beautiful geometric argument called line shelling. Bjorner has that independence complexes of matroids are shellable, and that will come up later in the talk. And for us, very relevant are that the skeleta of complexes that are shellable are also shellable. So notation here is delta is the K-skeleton of the simplex on n vertices. Already deciding whether complex is shellable can be pretty difficult. The problem is NP complete, as was proven quite recently by Guak and et al. But we're going to look at even a smaller class of complexes. I said earlier there could be more than one way to shell the complex. So we're interested in complexes for where there's a lot of ways to shell them. So this leads to the notion of extendable shellability. A complex is extendably shellable if any shelling of a solved complex can be extended to shell the entire complex. That is, there's no subcomplex, no shellable subcomplex at which the shelling is stuck. There's some examples of this, but I would say rather fewer. We have some spheres are extendably shellable, so two-dimensional triangulated spheres like Danraj and Fee. Bjorner Eriksson proved that all rank 3 matroids are extendably shellable. And in general, for a d-dimensional sphere with just a small amount of vertices is extendably shellable. But when you start thinking about other simplicial spheres, like if you look at 3 spheres, you tend to lose this property, as Orca Ziegler shows. And you can come up with some very small counterexamples, I think even on 6 vertices of shellable but not extendably shellable complexes. So one question we thought when we started this work was, there's this conjecture of Simon that's almost 30 years old now. And it asks for just a very simple class of complexes. It asks whether they're extendably shellable, particularly the K skeleton of the N simplex. So this is what we wanted to know. And there are some cases known. The K equals 2K follows, I think, from the work of Bjorner and Eriksson from the uniform matroid. K equals 1 is just graph. It's the complete graph. It's fairly straightforward. And for higher K, close to the number of vertices, we do have extendable shellability, particularly for K greater than equal N minus 3. That's been proven by a couple different groups. So as we were thinking about this problem, we eventually made a definition that was useful for us. We say that a pure complex on N vertices is shelling completable if there's a shelling of delta, that's the initial sequence of a shelling of the D skeleton of the N simplex. That means delta is a shellable complex, and if you reach delta in the process of shelling the D skeleton, you're not stuck. So that shelling can be extended and completed. The actual shelling of delta doesn't matter, as long as there is one. So using this definition, we restate Simon's conjecture to mean that any pure shellable complex is shell incompletable. So we weren't able to prove that. It's still open, but we were able to prove that the nice subclass of Vertex decomposable complexes is shell incompletable. Oh, I should add that all the other cases of Simon's conjecture are still open. Okay, so first I'll do a relatively straightforward example, a shifted complex. Remember, a shifted complex has this nice ordering of vertices such that given the face in the complex, if you replace one of the vertices with a smaller vertex, you get another face in the complex. And you can check that with this example on 6 vertices here. So if I replace 2, 3, 5, if I replace 5 with 4, I check 2, 3, 4 is in the complex. And 1, 2, 3 must be as well. In general, if you have a d-dimensional shifted complex, then you can add the Revlex smallest missing subset to get a shifted complex. This is just a fairly intuitive fact. Just a reminder of what Revlex means. It's sort of the reverse dictionary ordering. We'll use it again in a minute. So in this case, we could add the Revlex smallest missing 3 set is 2, 4, 5. So we can add that, and then you can easily check that the resulting complex still has the shifted property. For our purposes, the useful thing about shifted complexes is that they're shellable. So by this property in the second bullet point, we have that shifted complexes are shell incompletable. So that definition holds for a fairly nice but strict class. Brief reminder, some vocabulary words. Simplicial complex, you have a face F. The link is the set of faces disjoint from F whose union with F is in the complex. And the deletion of F is the set of faces not containing F. Here we have a complex on the lower left. You take the face, which is just the vertex A. Look for the link. The link is shown on the bottom right. And the deletion of that vertex would be the union of the 2 facets, BCE and BCD. And one useful fact for us is that the link of a shellable complex is itself shellable. All right, so we were most interested in this subclass, vertex decomposable complexes. Definition is inductive, so delta is vertex decomposable if it's a simplex, or there's a special vertex, which we'll call the decomposing vertex. There's some disagreement about that in the literature. And we ask that V, either both its deletion and its link are vertex decomposable themselves. And we also want that every facet of the deletion of V is still a facet of delta. That just means that V is not contained in every facet of the complex. So we eventually found that these vertex decomposable complexes were a lot easier to work with than extendable shellability. So here at the bottom, we have some known facts. They were introduced also 30-some years ago by Prova and Bolera, along with K decomposability, which we'll talk about later. They're important because they are shellable for us. The K skeleton of a simplex is vertex decomposable. Shifted complexes are also vertex decomposable. Prova and Bolera showed matroid complexes are vertex decomposable, and you can actually use any vertex as the decomposing vertex. But as a non-example, we have Bergman complex of matroids. So here's our main result that we proved. The result says that given a d-dimensional simplicial complex delta that's vertex decomposable and it's on ground set V, then there is some linear ordering of the vertex set such that you can add the Revlex smallest d+1 subset not in the complex to get a complex that is still vertex decomposable. In other words, we can extend the complex by one d+1 subset to get a complex that is still vertex decomposable. And a very important immediate corollary is that vertex decomposable complexes are shell incompletable, right? Because the fact on the previous slide that said vertex decomposable complexes are shellable. So this also tells you that any counterexample to Simon's conjecture would require a complex that is not vertex decomposable. So I'll talk about sort of the idea behind the proof. I won't go into too many details. I have a couple examples. The proof is on induction, both on the number of vertices and dimension. Basically, given the vertex decomposable complex, you have a decomposing vertex. You check its deletion first. If the deletion is not full, that is, there's a facet missing, well, then you can use induction and apply to the deletion. And that says that, oh, I should add, deletion is vertex decomposable by definition of vertex decomposable. So you can extend the deletion to another vertex decomposable complex, and that facet you extended by is the one you need. Otherwise, you have to consider the link, and then induction allows you to extend that. So the main work of the proof is just the casework, but this is the basic idea. So first example, we have a complex on 7 vertices, 3-dimensional, and you know that 7 is a decomposing vertex. You check its deletion. It's not full, so by induction it has a decomposing order, and you can add the facet 1, 3, 4, 6. Next, I give you a different complex, delta prime. That's on 6 vertices, and it does happen that the deletion is full, so you can check the link instead. Use induction on that, extend the link by 1, 3, 4, and then we also must include the vertex 6 because we have to add a 3-dimensional facet. So the first application of results I'd like to talk about is to matroids, particularly the independence complex of matroids. I guess definition here, you're probably familiar with matroid is a set of facets with this exchange property where given two facets, a delta, vertex in one but not the other, then there's some vertex in the other but not the first, such that you can switch x and y and still get a facet of M. Matroids have, among many other properties, they're vertex decomposable. So by our result, they're also shell incompletable. So a question we asked after that was, well, is there an easy way to know what facets can be added? So the proof is not, the result is not algorithmic. So it just says that there is some ordering of the vertices that allows you to extend, but doesn't tell you what that order is. But it turns out for matroids, it is fairly simple to get that order. So the proposition here says, given a rank D matroid, as long as you order the ground set such that the first D vertices are in the complex, then you can add the revlex smallest D subset that's missing. And that will work, and the complex you get is vertex decomposable. So we did want to ask a related question was, can we extend the matroid and actually still get a matroid itself? But this only happens in a specific case. I think there's a typo here. I think delta needs to be a certain kind of matroid called a circuit hyperplane. So this is not true in general. The next application we were interested in was on complexes with co-few vertices. So there are some results in this area that are already known. In general, for a D-dimensional complex on D+3 vertices, extendable shellability is the same as shellability. So that was proved by Culbertson et al. I think like 2 years ago. And we found that actually we can strengthen that result a little bit, and that in this situation, shellability is actually the same thing as vertex decomposability. A consequence of that means that for these complexes, notions of shellability, extendable shellability, shell incompletability, and vertex decomposability are all the same. So it's nice to see these different definitions coinciding here. Unfortunately, this theorem is tight. There's some very small counterexamples. The one that I mentioned earlier, there's complexes on 6 vertices that are 2-dimensional, shellable but not vertex decomposable, and some that are not extendably shellable either. So last thing, I'd just like to talk about some further directions in our research. There is a notion, I think, also defined in the original paper on vertex decomposability. K decomposability is a more general notion. You ask that the complex has a face, which is called a decomposing face, dimension less than or equal to K, such that its dilution and link are both K decomposable, and also any facet of the deletion, that face is a facet of the complex. So this definition is nice because it interpolates between two of the concepts we've seen above. So showing the chain of inclusions in the middle here. We got zero decomposability is the same thing as vertex decomposability, so on up into de-decomposability, which is the same thing as shellability. So a natural further question we'd like to ask is, can we extend a K decomposable complex by one facet to preserve K decomposability? So that's a natural generalization of our main result. So our result is K equals 0. When K equals D, this would just be Simon's conjecture itself. But this question is still kind of hard even for K equals 1. So I think the case of one decomposability is still an open question. It's work in progress. Okay, that's all I have for today. Thank you.
All right, thank you very much for your talk. Are there any questions? Okay. Doesn't seem to be the case.
Okay.
So thanks again.